In this video, we discuss learning outcome number 3 for lesson 10.2, which is about a strategy for finding the best predicted Y value given a particular X value. When I thought about this material, the first thing that came to mind was good idea, bad idea. I don't know if any of you guys remember from the 90s. There used to be a cartoon called Animaniacs, and they would do this bit called good idea, bad idea. And they'd say, good idea, do this, bad idea, do this. And they were very similar, related, but sometimes it was a really, really bad idea. And sometimes in some circumstances, it was a good idea. And that's exactly what came to mind for me when I started thinking about using this regression line or using the regression equation, the equation of our regression line to predict Y values. So it is a good idea to use the linear regression equation to make predictions of Y values when we have evidence of a linear correlation. Because if we have evidence of a correlation, a linear correlation between the two variables, then we're saying that the Y value and the X values are related in some linear fashion. So it makes sense in that case to use the linear regression equation to predict Y values for given X values. Now there's one other qualifier. In addition to having evidence of a linear correlation, we should make sure we have an X value that is within the scope of values used to find the regression equation. We don't want to go off too far to the right or too far to the left. We don't want to choose X values that are very high compared to all the X values that were used to come up with our equation. And we don't want to choose X values that are extremely low compared to all the X values that were used to come up with our equation. We want our X values to be within that range of X values that we started with so that that linear approximation of the data is appropriate. We're never 100% sure that that linear pattern is going to continue as we keep going in either direction. So provided that the X value is in the scope of values and we have evidence of a linear correlation so that that scatter plot fits our data really well, then it is absolutely a good idea to use that linear regression equation to make predictions for Y values. And you can imagine what the bad idea is. It's a bad idea to use the regression equation to make predictions when there's no evidence of a linear correlation between the variables. If we're using this regression equation, which is the equation of a line that's describing the best fit relationship between X and Y, but there's not actually a linear relationship there at all. Even though we can use those formulas that we discussed in the last video to come up with B sub 0 and come up with B sub 1 and come up with this equation for any set of ordered pairs, if there's not actually a linear relationship, we shouldn't use the equation of a line to make predictions. So it's a bad idea to use that regression equation when there's no evidence of that linear relationship. In that case, if you're trying to find a Y value and you're saying, what's the best guess for the Y value then if I can't use that equation? The best guess that we have for the Y value is the sample mean of the Y values. Remember, that was our point estimate of the true population mean. And that point estimate of the true population mean was an unbiased estimator. Remember, we expect it, the expected value of Y bar is actually the population mean. And so if I don't know anything else, if I don't have evidence of a linear correlation, the best guess I have for what Y is the sample mean, because the average Y value is the best representative of Y, given that we don't have any evidence of some other kind of correlation. So that's what came to mind for me. Now, I just said all of this, but I just wanted to put it on a slide. In other words, use the regression equation to make predictions under these circumstances when you have evidence of a correlation between the two variables. And if you're saying to yourself, when do I have evidence of a correlation between the two variables? Remember this from 10.1. If the absolute value of R, that's our linear correlation coefficient, is greater than the absolute value of those critical values of R. Remember, we have two critical values when we're looking for evidence of a correlation, one in the left tail, one in the right tail. If the absolute value of R is greater than that critical value, that's saying that our R value is farther out in the tails than our two critical values are. Or in other words, that R value is closer to 1 or -1 than our critical values are. So then we're saying we have evidence of a correlation, sufficient evidence of a correlation for the particular significance level that goes with that critical value of R. So we need that. We need evidence of a linear correlation. And then, of course, we also need the data to not go too much beyond the scope of the available data. If we go far beyond the scope of the interval of x values for the data set that we have, that's called extrapolation. That sometimes makes sense. If we have reason to believe that that linear relationship continues to hold on a larger interval of x values, go for it, go ahead and extrapolate. But if we don't have any evidence or any reason to believe that that linear pattern continues to hold, we shouldn't expect to be able to plug in very, very large x values or very, very small x values that go beyond the interval of x values that was used to come up with that regression equation in the first place. Because the truth is, at the extremes, that pattern may not continue to hold. So we need to be very careful about extrapolation. We should only extrapolate when we have reason to believe that extrapolation will give us a good estimate. Now, if you do not have evidence of a correlation, or your x value goes far beyond the scope of the available data, then you shouldn't use the regression equation to make predictions. In that case, the best predicted value of y, regardless of what x is the sample mean y bar. This is just a visual that describes exactly what I described on the last two slides. Mr. Triola adds this point. He says the regression line graphed in a scatter plot should show that a line fits the points well. So we shouldn't just assume that because we have a linear regression equation in a particularly high value of r, that the data are best approximated by a line. It's possible for that data to form maybe like the shape of a quadratic function, a parabola, and still have an r value that would show evidence of a linear correlation. So we really need to be careful about that. When we're actually doing this in practice, if I'm trying to decide whether or not to use my regression line, it's always a good idea to graph that scatter plot and graph the regression line together and see if the scatter plot actually looks like a line is the best model to approximate that data. Now, if that line fits the scatter plot well, and we have evidence of a linear correlation, and the x value that we have doesn't go too far beyond the x values that we started with, then we say, yes, the regression equation is a good model. The data looks like a line, and we're in this interval where the data looks like a line. So it makes perfect sense to use the equation of a line to come up with that predicted y value. Now, if any one of those does not hold, so the scatter plot does not fit a linear model, or we don't have evidence of a linear correlation, or we're choosing an x value or someone's giving us an x value that's far beyond the scope of x values that we started with, then it's not appropriate to use that linear model to predict anything. If there's not a linear relationship, don't use the equation. That's exactly what this is saying. So if we don't have a good model in our linear regression equation, then we just use the sample mean, y bar. That's the mean of the y values. It does not matter what x is. The best predicted value of y at that point is the average y value, or the mean of the y values, arithmetic mean. Okay, so let's do a couple of examples in which we use these ideas. Now, I'm not actually coming up with the regression equation, the r value, or y bar myself in these examples. These have been provided to us. In practice, sometimes you actually have to compute these. So let's look at our first example. It says, using 6 ordered pairs of data for internet use and Nobel Laureate rates, we found that the regression equation was y hat equals negative 8.4430 plus 0.2028 times x. We found that in the last video when we came up with regression equations using those 3 methods. That was the equation that we came up with 3 times using 3 methods. We get the same thing every time. In that process, when we were coming up with y hat, we computed y bar at one point. It was 5.067, and we needed to compute the linear correlation coefficient r in order to find b sub 1 at one point, and that was 0.799. Given all that, the question says, find the best predicted Nobel Laureate rate for Japan, which has approximately 79.1 internet users per 100 people. And we want to do this using a 0.05 significance level. Now it's really tempting to just go ahead and plug in 79.1 into that equation. Just plug this in for x and see what y is. Don't do it. You need to check and see if there's evidence of a linear correlation first. With 6 pairs of data, it's a tough bar. It's a high bar. That linear correlation coefficient r is going to have to be really high when our sample size is so small, n equals 6. But we'll see if we have sufficient evidence of a linear correlation with n equals 6. Okay, and then after we do that, the question says, how does that predicted Nobel Laureate rate for Japan compare to Japan's actual Nobel Laureate rate of 1.5 per 10 million people? So they have 1.5 Nobel Laureates per 10 million people in Japan. And say, okay, well, how does that compare to our prediction? Well, first we've got to do the prediction. Okay, so we'll start by deciding whether or not we have evidence of a correlation between the two variables. That requires coming up with our R value, which was given, and then identifying alpha and n. Alpha is our significance level, which happened to be 0.05, and our sample size was 6. We were told we had 6 ordered pairs, and we saw those 6 ordered pairs in the last video where we came up with that regression equation. Now that we know that alpha equals 0.05 and n equals 6, we can find the critical values of R using table A6. So this is table A6, n is equal to 6. Alpha is equal to 0.05. Oops. Here we go, and I want to draw on this. So if n is equal to 6 and alpha is equal to 0.05, it looks like our critical value of R, positive critical value, is 0.811. Now we have 2 critical values because we're saying, the null hypothesis is that there's no correlation. The alternative is that there is a correlation and we don't care if R is too high or too low. On either side, we want to say, rho is equal to 0 or rho is not equal to 0. So this is a two-tailed test. And the critical values of R are plus and minus 0.811. So we've got our critical values now. Now we want to compare the absolute value of the critical values to the absolute value of R to decide if there's evidence of a correlation. Remember, if we graphed these on a number line, the values of R in between the 2 critical values do not provide sufficient evidence of a correlation, whereas an R value that is more extreme than the critical values, that's farther out in the tails, that's closer to 1 and closer to -1 than our 2 critical values are. In that case, we would say that there's evidence of a correlation. So we just compare these 2 absolute values, and that tells us the same thing. Since the absolute value of our R is 0.799, and that's less than this 0.811, the absolute value of both of our critical values, that means the R value is in between the 2 critical values. And that means we don't have sufficient evidence of a correlation at the significance level with this sample size. If we made the sample size larger, the critical values would come down a little bit. So maybe we could have sufficient evidence of a correlation with a larger sample size. That's possible. But with this alpha level, with these 6 ordered pairs, we don't have sufficient evidence of a correlation. So that means it is a bad idea to use the regression equation to approximate anything. We don't have evidence of a linear relationship between the 2 variables. So we absolutely should not use the equation of that line to predict anything. Since we don't have evidence of a linear correlation, the best predicted value of Japan's Nobel Laureate rate, regardless of the X value that they had, is y bar equals 5.067. That's 5.067 Nobel laureates per 10 million people. That's actually very different. 5.067 is very different from 1.5 Nobel laureates per 10 million people. That's what happens. That's what you do if you don't have sufficient evidence of a correlation. You go and you use y bar. Now let's look at another example. If we used 23 ordered pairs of data for chocolate consumption and Nobel laureate rates, we could compute the following statistics. Y hat is equal to -3.37 plus 2.49 times X. Y bar, that's our average Y value, is 11.104. And our R value, that's our linear correlation coefficient, is approximately 0.801. Now we're asked to find the best predicted Nobel Laureate rate for a country with a chocolate consumption of 10 kilograms per capita using a 0.01 significance level. So we're doing the same thing as we were doing before. X is the chocolate consumption in a number of kilograms per capita. So they're asking us to predict a Y value, predict the number of Nobel laureates, given that X equals 10 kilograms per capita. You might be tempted to just plug in 10 to this, but don't do it. You have to check if there is a linear correlation between the variables first. If there is a linear correlation, go ahead and use the line. If there's not evidence of a linear correlation, go ahead and use Y bar, use the sample mean. But you always have to check and see if there is evidence of a linear correlation first. And that linear correlation depends on the significance level. Okay, so let's decide whether or not we have evidence of a correlation. We've got our R value, it was given to us. We need to identify alpha and N. We were told that alpha equals, is that 0.01 on the last slide? I think I had it was 0.01 for this data set. And a sample size of 23. We were told that we had 23 ordered pairs that led to that value of R and Y bar and that regression equation. Now that we know our alpha and our sample size, we want to use table A6 to find the critical values of R. So let me show you how to do that. Now in table A6, we actually don't have an N of 23. We have 20 and 25. In order to be conservative, we're always going to round down here. And so with alpha equals 0.01 as our significance level, the critical values of R are plus and minus 0.561. Okay, so this is what we have. We just need to compare the absolute value of the critical values to the absolute value of R. I think we can all see that our linear correlation coefficient has an absolute value that's greater than our critical values, or the absolute value of our critical values. Since our R value is closer to 1 or -1 than those critical values are, that means we have sufficient evidence of a linear correlation at this level. So it's absolutely a good idea to use the equation of that regression line to estimate something, to predict the Y value given a particular X value. Since we have that evidence of a correlation, we just need to plug in the X value to our Y hat formula and find out what Y should be. We were told that this country has consumes 10 kilograms of chocolate per capita. Then the best predicted value of the number of Nobel laureates in that country is -3.37 plus 29 or 2.49, excuse me, times 10, which is approximately 21.5 Nobel laureates per 10 million people. That is our best guess for what their Y value is, what the number of Nobel laureates should be in that country, given that their country consumes 10 kilograms per capita of chocolate. Now, if we actually knew how many Nobel laureates that country had, we could compare and we could find out if this model was any good, at least for X equals 10. But in the absence of information, we just know that this should be a good model because we have sufficient evidence of a correlation at this significance level. So that's it for our discussion of predictions using the regression model when appropriate and using Y bar, the sample mean, when not appropriate. In the next video, we'll talk about outliers and influential points and whether a particular point is an outlier or an influential point when you have a scatter plot.